Some quick announcements before we get started. We have a couple things due on Friday. We have our homework one redo and the most recent assignment of implementing sorts into our linked lists. I wanted to take a quick second and remind people that I'm expecting the sorts to be inside of the objects, not as something that these sorts that the objects refer to. So each object, the singly linked list object, should have a method called selection sort, and a method called insertion sort, and a method called bubble sort that is the optimized bubble sort.
What about those like overriding like the list interface?
It shouldn't be necessary. You should just be able to, you can add them to the list interface if you'd like. But you can add additional functionality to something that's not in the interface, but if you put it in the interface, then it has to be in everything that implements that interface. So either way there is probably fine. Since we're putting it in every list, you could just throw it in the interface as well. So that way your driver can make one of the objects. So you're going to query the user, what kind of linked list would you like? Singly, doubly, circular doubly, whatever they say, you're going to instantiate the associated object. And then you can ask them, what would you like to do with that object? You can add, remove, etc. But eventually, once it's time to sort, you're going to call that, let's say you call the object a constructed list. You would just say list dot, if they select the selection sort, list dot selection sort, because that's going to be a method inside of the selection sort object.
How would you like us to implement, like, where you put the user for input, like, how would you like us?
Some kind of command line application. So it just should be, you type through the prompt that appears. So yeah, it's pretty typical input output procedure for that. I would like to get people some experience with file IO because I know that is on the 8th. But I don't think it really makes sense for this project in particular. So I'll figure out some place for that, even if it's just something we talked about before people take the 8th. That leads us to the second announcement that the first 8 study session hosted by the ACM Club is today at 2:30 down in the lab downstairs. I highly recommend people attend. I will be attending as well to be able to answer questions. So it's a great place to tackle whatever you feel like you are weakest at on the practice apes, etc. And maybe I can make that a little bit easier for you. Maybe some of our upperclassmen can make that a little bit easier for you. So let me know how we can be useful, and hopefully I see you there. Last time we got additional practice with recursion. We were implementing binary sort recursively. Did anybody get that working between yesterday and today? 1.5 people? Better than 0. So we're going to start off today's class by implementing it and talking about how to actually go about it. So rather than slides, we're going to be in our flips. So we're going to call this what? Binary search. Sure, and that way we could decide to make it iterative or recursive. Let's make a method that is going to be recursive. Binary search is going to return the index where we find it. So it should be an int. So if the needle is in the haystack, we want to return the index of the haystack where we found the needle. If not, we want to return some value that makes no sense. Where could the needle not be? For any array-based system, index -1 makes no sense. It does not exist. It's not part of any list of any size. So we're going to return -1 if we fail to find. So we'll call this binary search recursive. It's going to take 4 things. We need to take the query value. Actually, let's call it the needle. We're going to take the array, we'll call that haystack. Then we're going to pass in L L looks very close to a one, so maybe we call this left and right. That are gonna be the bounds, the index bounds of the current array. Those should be all we need in order to calculate everything that we need to figure out is the needle at the middle index. In order to answer that, we need to figure out where the middle index is. So that's probably the first thing we want to do is make a variable we're gonna call middle. What expression will get us the middle of the current haystack? We have left and we have right. How do we calculate middle?
Plus right divided by 2.
Yeah, it's the average of them. So we want left plus right over 2. What happens if I don't put the parentheses there? Yeah, we're gonna take right over 2 and then add left, which is gonna give us a very different index. We have to make sure we keep track of order of operations. That will be very important here. So identifying the middle. The first thing we should figure out is this out of bounds? Well, maybe we want to come back to that. Let's figure it. We'll come back to it. That'll be the last thing we write. I kind of want it to come first, but I think through the course of identifying the other cases, it'll be easier to identify the error case. So if it's not the error case, we could have located it. What is it like? What should I write if the needle is found at this middle index? So we first need to identify the case. So if what? Yeah,
In case that, I guess where brackets middle equals.
the haystack at the middle is equal to the needle. If the thing we're looking for is the same value as the value at the middle index in the list that we are looking for, then we want to return what? We want to return, yeah, middle, which represents the index into the list where we found the needle, which is what we are looking for. Great. Does this need to be an else if? No. Why not? We have a return. So if we hit this if, we're done. We don't need to worry about hitting this. If we hit this next if, it's because the prior if failed. So now we need to figure out, all right, if the needle wasn't at the middle index, is the needle in the left half of the array, or is it in the right half of the array? Let's focus on the left half first. How can we identify whether, since we know that the haystack is sorted, every element is in increasing order, how would we identify that the needle is in the left half of the current array?
If needle is less than haystack middle.
If that's the case, then we want to do what?
Set middle last.
So we want to call binary search recursive. We're going to need to identify what the new values of left and right are as we identify those. But rather than modifying left and right, which is what we want to do if this were iterative, we would want to be preparing for the next pass through the loop by setting our variables to those values. We want to modify them as the parameters that we're passing into the recursive call. So we want to call binary search recursive, and the needle and haystack stay exactly the same. We want to pass the needle on, we want to pass the haystack on. What changes are the values of left and right. So if it's in the first half, how does left change? It stays the same. Does that make sense? The beginning index of the array is still going to be the beginning index of the new array if we're looking at the left half of the array. only the right is going to be moving down to say that we have a smaller array than the last time. So how does right change? Yeah. We know it's not the middle, so the new rightmost element that it could be is one before the middle. Now, binary search recursive returns something. So we can't just call binary search recursive here because we would be throwing away the result. What should we do with the result of this recursive call to binary search recursive? Yeah, we just want to return it. Does that make sense as to why? If we identify where it is recursively, we just want to pass that back up through the recursive chain. So we're just straight up going to return it. On the other hand, I don't have to do it like this. How do we identify that it would be in the right side of the array? Do we need this if statement? We actually can straight up delete it because we have three cases here. It's either founded at the middle element, it's less than, or it's greater than. And those are all of the possible cases. Do we agree there's no possible way that we would not be in one of those three cases?
Well, it's not on the list, but.
Yeah, so if we're gonna identify that up top here when we get to it, but that's a great point. But even if it weren't in the list, then it still has to be either less than, greater than, or equal to. It may be so much greater than that it's not in the list, or so much less than that it's not in the list. But so we actually don't need this logic at all, and we can just straight up say return binary search recursive. What changes now? So this is for the case of it's in the right side of the current array. So which of these change? Left changes. What does the left become? Middle plus one. If it becomes part of the right part of the array, then it's not going to be the middle, but it could be the middle plus one. That is the lowest element that it could be. Great. These are the correct three cases for we found it. It's in the left half or it's in the right half. How do we identify that it's not in the array at all? Yeah, so eventually, as we do this, we're going to end up with a single element. We're going to be querying, is the needle exactly this one element in this array of size 1? When we recursively call this, we're going to be saying that either the right is middle minus 1 or the left is middle plus 1, which is going to either make left greater than right or right less than left by moving one of those in that way. As we do this, we're going to come up with a Boolean expression that will tell us that we failed to find if left and right are out of order. If right ends up being left less than left, then we have an array of size 0. We failed to find in our array. So then we can come back up to this and say, if right is less than left, something is horribly wrong, we failed to find. We'll identify that we failed to find by just returning -1. So let's test this out. We should write a quick driver for it. if you were an IntelliJ and want a quick way to do main like this, you just type PSVM tab. Public static void main, PSVM tab should give you the entire main method. Just like SOUT tab should get you system.out.println. Oh no, you just hit, you would type like PSVM right out here. PSVM and then just hit tab. And that should do it. Does that work for this? No, it does not work in Eclipse. I have to type main and then instead of tab, it's control plus space at the same time. But each IDE has some way of taking these long things and just making them a lot easier to type because you end up typing main a lot. You end up typing system.out.println a lot. And Java is just super verbose in its. So it's nice to have some kind of shortcut for that. All right, so we did want this int array. What do we want to call this? Doesn't matter. So this needs to be sorted in order for this to work. So let's just do something silly. And we'll make an array. And we want to search for this. So let's print a call to binary search recursive where we're going to pass, let's try to identify 7, the array. The left is always 0 when you do this, and the right is going to be the array's length. -1 is we want 9, there are 10 elements, and we want to go from 0 up to and including 9. So that should find that. And then let's also test this with something in the left half. Maybe we search for 1. And again, we will copy from 0, the index, up to the length -1. And then we'll try to find something that's not at all in the list. Like 50. All right, we should probably, before we do this, add some kind of string to this so that we can know exactly what it is that we are looking for. So I like that. But here we are searching for 1, and here we are searching for 50. Great, very basic test for us. We run this and oops, we have an extra space. Result is index 6, that's where we expected to find the 7, since it should be offset by 1. Searching for 1, the result was index 0, which is what we expect. Searching for 50, the result is index -1, which we expect because it wasn't in the array. So I'm reasonably happy with this. This seems to make sense. It didn't take an incredibly long period of time to be able to identify it. Does anyone have questions about binary search, the recursive implementation of binary search?
How we did the boundaries, we didn't set up array like -1, we just did one here, right, but it kind of just.
So that's a good question. If there are 10 elements here, if we look for the middle index here and we say left plus right over 2, if right is 1 too high, what happens?
The middle is,
The middle could be wrong. It depends on whether your array is even or odd length. One time it'll get it right because integer division is nice like that and it blocks off the remainder. And the other one, you would incorrectly identify the middle element. This would be another example of where you might want to have a private method that gets called here. And that way, when you call this, you call it and then identify what the appropriate left and right should be. And that way your user can't accidentally pass in the wrong value here. If you pass in the wrong value here, it's not going to work. So I think this would be better implemented as a private with an overloaded one that just takes the needle in the haystack. Because the user shouldn't need to figure out what the left and right should be. The left is always going to be 0 and the right is always going to be the length of the array minus 1. So let's actually implement that just so we can, just so I can show you what that looks like. We would just have a public static int binary search recursive that takes just the needle and the haystack. That's it. There. So we want to return a call to binary search recursive with the 4 parameters where we pass in the needle, the haystack, 0, and haystack dot length minus 1. And then here, rather than calling these, we can now just straight up remove the last 2 parameters and they get added in the other method. Touchpads are the bane of my existence. And we see that we changed nothing. Works exactly the same, and now the user can't mess it up. They just pass, what am I looking for? Where am I looking to find it? And we have hard coded now the 0 and length minus 1, because those are never going to change. Note that outside code now can't call binary search recursive. I was able to call it here because we're in the same class. And the same class has access to private methods in the same class. But if we were using this outside of this class, we would only be able to interact with this method and not this method. Cool. So the rest of today is going to be spent on the last one, the last recursive problem that I'm planning to go over. I guess we should probably figure out the recurrence relation for the binary search. How large is the problem? Is the new problem after we find this? So if we were to construct this, we would say the time that it takes to solve something of size n equals what happens when we solve something of size n? What is the associated call that we do? What's the size of the array based on n? It's T of n over 2. So we're basically saying we have an array of size n. Our array of size 10 was what we started with in our example. When we first look at the middle, we're going to look at the index that's in the middle of that. And then we're either going to call it the left half or the right half. The left half is going to be of size 5 and the right half is going to be of size 4. No, it's the other way around. Left half is going to be of size 4, right half is going to be of size 5. So we're basically cutting it in the worst case in half. How expensive is it to do this process? How many operations do we need in order to cut the size of the problem in half? Yeah, it's really a constant number. We're checking the comparison for, is it in the left half? Is it in the right half? Is it the error case? Is it did we find it? So depending on the order that we write these in, it's either +2, +3, +4. I'm just gonna write +1 because it's constant. And it doesn't actually really matter what the value of this is unless it depends on n. So if we were to write out this recurrence relation and try to come up with an expression for it, what would we find? So let's write a few examples of this. T of n is 2. We're going to start n out at 2. I can also write that T of 1. When we come up with an array of size 1, there's only one operation to do. We either found it or we didn't. So T of 2 is going to be T of 1 plus 1. So T of 2 is 2. What happens if we change this to T of 4? We end up with 3. What happens if we change this to T of 8? What do we notice? It should be 4. Because we 8 divided by 2 is 4, so we take the value that's already here and add 1 to it. Every time this doubles, we're going to be adding 1. Every time this doubles, we're going to be adding 1. So what is this process, or how expensive is it to do this? It's based on what function? Good guess. It's the log, yeah, and this is logarithmic. So if you subtract 1 from each of these, we get 2 to the first equals 2. We get 2 squared equals 4. We get 2 to the third equals 8. We get 2 to the fourth equals 16. So we're just 1 more than the log, always. So it's going to scale at a logarithmic rate. Even though I'm using exponential here, the variable we care about, this is the length and this is the time. Since the time is less than the length, it's logarithmic and not exponential. It's the inverse of the other. If we had T of 3 equals 4, T of 4 equals 8, T of 5 equals 16, that would be exponential. But it is the inverse of that, showing that the log of this is proportional to that. Log base 2. Does that make sense? You'll get much more of this in algorithms. I just want to start to get you thinking about complexity, thinking about how complexity maps to mathematical functions as you analyze and as you start thinking about recursion. It's not easy to wrap your mind around at first, but it'll come. It'll come with time to practice. All right, last recurrence. Is anyone familiar with the towers of Noye? You've probably seen it before. This is really going to test my ability to draw at more than a second grade level. So this is the game that has 3 pegs. And we have some number of, oh gosh, drawing circles is hard. We have some number of differently sized circles that are on this first peg. And the idea is to move everything from the first peg to the third peg. But you cannot move anything. First of all, you can only move one at a time. And you can't move something that is larger, or you can't put something larger on top of smaller. So to solve this, you would move this here, so you would move the small one here, get rid of it here. You would move the medium one here, getting rid of it here. You would move the small one here, and I've already messed up because this should be moving here and not there, so I've missed where this should be the first time. But the idea is that you move the entire stack over from the first peg to the third peg. So here is something for you to do momentarily. Go ahead and go to this very non-American site, Maths is Fun. It's either British English of some kind, because they pluralize math. So mathsisfun.com/games/Tower of Hanoi, and play it for like 5 minutes. Solve one of size 3, solve one of size 4, and then start thinking of something like Towers of Hanoi of size 8, size 9, as large as it can be, and think, how much extra work, how much harder is it to solve this game as it is larger than that? Solve it for 3 and move up to something else. How's it going for people? Five's challenging. Five's a little bit challenging. Five's- So. You can see that the minimum number of moves for towers of Hanoi 8 is 255. If you do it optimally, perfectly, it will take 255 moves to do this. For a second, think about writing this code iteratively using loops. How many lines do you think the solution would be? Think about solving it recursively. How many lines do you think the solution is? It's really short. It's actually surprisingly really short. So your task for the remainder of today is to attempt to pair program this. See if you can come up with a Tower of Hanoi solver for an arbitrary disk size. So not just 8, this should solve Tower of Hanoi 20. It should solve Tower of Hanoi really beyond 20. It's going to be so many moves that it's going to be disgusting to even look at. But it turns out that you can see that this is an exponential decay. Like it takes twice as many moves to solve one more disk than it does for the previous disk. So see if you can make this work. And my hints as you get started with this is 1, don't overcomplicate it. The solution is surprisingly simple. And remember that when you call something recursively, when it returns to you, it's magically done. As long as your logic is correct for this size, then it will work for every size that is smaller than that, as you prepare yourself to do that. So how would we solve Towers of Hanoi 8 if Towers of Hanoi 7 were just solved for us? What would the steps be of solving this problem?
How do you quantify the disks?
We either number them or letter them or something of the sort. Yeah, we have some list of. Assuming Towers of Hanoi 7 is solved. How do we solve 8?
You just switched to
Yeah, you switch the tower that we're trying to aim for. So we take the entirety of Towers of Hanoi 7 and we say, move that here. However that happens, just assume that it's solved. Then we take disk 8 and we move it here. And then we solve Towers of Hanoi 7, which is already on this stack, and move that here. Done. And that solves Towers of Hanoi 8. To solve Towers of Hanoi 7, that's going to be its own separate subproblem. Where if we wanted to solve this subproblem, we would take Towers of Hanoi 6, and we would say, move that here. Then take disk 7, move that here. And then take everything from disk 6 and move that here. That solves Towers of Hanoi 7, assuming that Towers of Hanoi 6 is solved for us. So think in that regard as you construct the solution recursively. You don't need to solve the smaller problem. Just solve it for size n, assuming that size n minus 1 will magically solve itself. And then the base case is when you have Towers of Hanoi of size 1, you will need to specify exactly what needs to happen when we have a Towers of Hanoi problem of size 1. Give it a shot. You got this.
So these are really absurd.
I would even put them as letters, or yeah, you can do this really however you reasonably think you would want to. I personally would use some kind of either array structure or some baseline. You can use an integer to represent capital A, and then you can use an offset to figure out which disk are we referring to. Are we referring to disk 5, in which case it's capital A plus 4. Something like that. Do we need it? If we're trying to solve powers of Hanoi of size 8, do we ever need to access any disk and refer to any disk other than disk 8? So do something like pass in a number. If you're trying to solve powers of Hanoi 8, then you can just access disk 8 and then towers of Hanoi of size 8 minus 1. Because you never need to access any of these other disks as part of that call. So you don't really even need a structure, I don't think. It's simpler than storing a structure. The reason I'm choosing this problem is because it is vastly different in complexity between iterative and recursive. So this is one of those instances where you would want to think recursively rather than thinking iteratively.
So the bottom of this would be this 8, the top would be this 1.
Yeah. So the bottom.
Like, either just show that it would be all the way over or on top of this.
Yeah, okay, so let's talk about this. Let's label each one of these. So this is going to be stack A, stack B, and stack C. So now if you're structuring this, what you need to pass in is something like, where is the current stack stored? Where is the destination stack? And which stack is going to be used to store the intermittent stuff? So we're gonna call it like the helper stack. So we have the from stack, the destination stack, and the helper stack. And then as you solve a problem that is smaller than that, you're gonna swap the destination stack and the helper stack. There are no lists whatsoever. All you should need is access to these letters and these numbers, of which you really only need the largest number for the current column. It should not return anything, it should print the sequence of instructions. So to print to the screen whenever you identify a rule. So the very first thing we should do for this is move peg 1 or move circle 1 to stack either B or C. And that is the first line that we should see printed. This is challenging. So I just want to put this out there that this is the hardest thing we have done yet in this class.
Are they great? Are they very?
Nope. You don't need to store anything in a list. So I would make a call to Towers of Hanoi and I would pass it 8. It would say solve Towers of Hanoi of size 8, and the assumption that we can make when we say that is that all of these disks are on A. And you should pass in something like, if we call this the we could label these as, we want to move this Towers of Hanoi from A to C using B as a helper. Then when we wanted to call it for size 7, like we said before, as we did this process, we would be moving 7 to the helper stack. So when we do this and want to recurse and solve this for Towers of Hanoi of size 7, this is going to be the from stack. You want to move the 7 to the 2 stack. This stays the 2 stack. But this becomes the helper stack. So these should be parameters to your call. Which stack is the from stack, the 2 stack, and the helper stack, so that you can successfully move them.
What types of like variables have this one does?
I would call this a character, because all you need is A, B, or C. What's gonna get printed to the screen? It would be like move disk 1 from A to C. And that would be the first instruction. And then you would say move disk 2 from A to B, move disk 1 from C to B, etc. And you would have, for Towers of Hanoi of size 8, 255 moves worth of prints. And I would argue that we can do all of this with about 6 lines of code.
Already.
Okay, maybe more than 6. 10 lines of code. It's surprisingly simple if you think about it recursively. If you don't worry about trying to solve 7, you just worry about trying to solve 8. 7 gets magically solved. out of time for the day, but my challenge for you is attempt to finish this off between today and tomorrow's class. We'll go over a solution at the start of next class, and hopefully that helps people to realize the power of recursion. We'll also look at an iterative solution and see just how much longer that is. It's kind of gross.